We are diving straight into Dr. Zero, self-evolving search agents without training data, a paper by Zenrui Yu, Kartikeya Upasani, and their collaborators from Meta Superintelligence Labs and UIUC.
Right, and the core challenge they're tackling is pretty critical for advanced LLMs. To get good at multi-turn reasoning and tool use, you need a ton of high-quality human training data, and that's just prohibitively expensive.
And the old self-evolution methods, they just couldn't quite cut it here, right?
Not at all. They tended to generate really low diversity questions, and frankly, they were computational nightmares.
So enter Dr. Zero. It's this unified data-free framework where an LLM can just autonomously generate and solve its own problems, getting more and more complex over time.
And the key thing is how it gets its supervision. It uses an external search engine, but only for verification. That search engine completely replaces the need for human annotated data.
What makes it all work are two huge technical breakthroughs.
Yeah.
First is this symbiotic proposer-solver feedback loop.
Yeah, it creates a dynamic, difficulty-guided curriculum. As the solver gets smarter, the proposer basically learns to write tougher tests for it.
And the second innovation solves that whole computational nightmare problem. Hop-grouped relative policy optimization, or HRPO.
This is the secret sauce. It clusters structurally similar questions together, and that just slashes the compute costs of the reinforcement learning, cutting down processing by about 75%.
And the headline result is, it's genuinely surprising. Dr. Zero shows that these complex reasoning skills can emerge entirely from self-evolution.
To the point where it matches or even surpasses fully supervised agents. We're talking up to a 14.1% relative gain on some pretty tough benchmarks.
It's a huge win for the zero data idea, and we'll get into this later, but a major insight is that the best curriculum actually depends on the model's size. That has massive implications for the future.
Okay, so let's unpack that. The whole idea of self-evolution with agents bootstrapping their own reasoning like R0, it's been around. It's a big paradigm shift.
All right, moving away from just static fixed data sets. But a lot of that prior work felt, well, a bit confined.
It was. It focused on narrow domains like math or coding. The problem structure there is pretty contained, so you can get away with generating kind of homogeneous data.
But open domain search is a whole different ballgame.
Exactly. The agent has to do multi-step reasoning. It has to use external tools like a search engine. And the previous data-free methods just fell flat because their proposers were, a bit lazy.
Lazy how?
They just default to generating simple single-hop questions. And if your training data is too easy, your solver never learns. It just stagnates. It never figures out how to chain multiple facts together.
So Dr. Zero is laser-focused on this problem for search agents in a zero-data setting. They get rid of all human intervention. No human questions, no human answers.
The whole process just relies on that external search engine, which they call R. The proposer uses R to find facts and then synthesize the ground truth for a brand new question it just made up. So R is basically the external supervisor.
So tell us about the architecture. You've got the proposer, that's pi theta, making the curriculum, and the solver, pi phi, learning from it. They both start from the same base LLM. How does that adversarial relationship actually work?
Think of it like a personal trainer who's also constantly inventing new exercises. The proposer's job is to create QA pairs that are difficult, but also verifiable. The solver tries to answer them.
And the feedback is just how well the solver did.
Exactly. The solver's performance tells the proposer if the question was too easy, maybe too hard, or if it hit that perfect sweet spot.
So the proposer is almost penalized if the solver either aces the test or fails completely. It forces it to operate right on the edge of the solver's current ability.
Precisely. It's an adversarial loop, but it's also symbiotic. The proposer has to get really good at using the search engine to build complex multi-hop questions, and at the same time, the solver is forced to develop better reasoning to answer them. The whole agent improves through this kind of self-play.
Okay, let's talk about that big technical hurdle. Because a search agent environment with tool calls and multi-turn stuff, it makes standard RL incredibly expensive. What was the exact bottleneck?
The bottleneck is all about how you estimate the value of a generated question. In standard methods like GRPO, you have to do something called nested sampling to get a good estimate.
Nested sampling. That sounds bad.
It is. It means for one prompt, you have to generate multiple possible questions. Then for each of those questions, you have to get multiple answers from the solver just to figure out how hard it was.
That sounds like an efficiency disaster.
Yeah.
Especially if you're hitting an external search engine every single time. The paper says it's an exponential blowup.
It doesn't scale. at all. And that's why hop-grouped relative policy optimization, HRPO, is such a masterstroke here. It gives you that low variance advantage estimate, but without the crippling cost of nested sampling.
So how does HRPO pull that off?
Instead of forcing all those expensive rollouts for a single query, it clusters the QA pairs it's already generated. It groups them by their cross-hop complexity.
You mean by how many reasoning steps or hops are needed?
That's it. You have a group of 1-hop questions, a group of 2-hop questions, and so on.
Okay, so if the proposer makes a new 3-hop question, instead of running 20 experiments on it, it just looks at the average success rate for all the other 3-hop questions in that batch.
You've got it. You're using the performance on structurally similar questions as your low variance baseline. This hop-specific normalization gives you a really efficient advantage estimate without that crazy multi-sample cost.
And that's what cuts the rollout cost down to about a fourth of what it would have been?
Yeah, it's the key that makes this whole thing feasible for complex tool-using agents.
That compute reduction is it's a non-starter without it. Okay, let's switch to the curriculum itself. We know it's about dynamic difficulty, but how is that actually encoded in the proposer's reward?
So the reward logic is all about the solver's current skill level. For a given question, they sample n attempts from the solver. And let's say k is the number of correct answers it gets.
And the sweet spot for the proposer is to generate a question where k is somewhere between 0 and n. The solver gets it right sometimes, but not always.
Exactly right. The proposer gets the maximum reward when exactly one of the sampled solutions is correct. If the question is trivial and k equals n, the reward drops to 0. If it's too hard and k is 0, the reward is also 0.
That's a really clever linear decay function. It gives this immediate, powerful feedback that's constantly pushing the proposer to challenge the solver without overwhelming it.
It is.
But hang on, if the proposer's reward is all about gaming the solver's difficulty, couldn't it just learn to, cheat? To find some weird exploit instead of generating genuinely good questions?
That is a critical point, and it's something the authors flag for future work, avoiding reward hacking. For now, they have a really important guardrail, the format reward, or RF.
That's a separate reward component.
Yep. It's worth up to half a point, and it just enforces structural validity.
Structural validity. You mean making sure it uses the right tags, like think and tool call?
Yes. If the proposer starts generating junk questions that are formatted incorrectly or don't use the search tool properly, it loses that reward. And that data is useless anyway. It keeps the system honest. It makes sure complexity is tied to real tool use.
So once a proposer uses HRPO to generate a batch of this high-quality, challenging data, it's the solver's turn. How does it get refined?
The solver, PyPhi, is trained using the standard version of Group Relative Policy Optimization, or GRPO. It just uses the synthetic data from the proposer. The reward there is super simple. It's purely outcome-based. You're only rewarded for getting the final prediction right.
So the proposer learns how to ask the right questions, and the solver just learns how to be correct. The whole curriculum is controlled by the proposer. That's fascinating.
And it's so efficient. They use an alternating optimization loop. 50 steps for the proposer with HRPO, then 50 steps for the solver with GRPO.
Oh, no.
The whole training is just 3 iterations. That's only 150 steps per model.
That's incredibly short.
It's only possible because the curriculum is so high impact from the get-go.
Let's get to the proof then, the hard evidence. How did the zero data agent actually stack up against models trained on expensive, human-curated data?
The experiments were pretty comprehensive. They used single-hop benchmarks like NQ, multi-hop ones like HotPotQA, and the 3 billion parameter Dr. Zero model. Well, it consistently matched or even surpassed its fully supervised baseline search R1.
Matched or surpassed.
Yeah. In one case, on NQ, the 3B Dr. Zero beat the supervised model by an astounding 22.9%.
Wow, that's powerful validation. And how did it compare to other data-free baselines like R0?
It wasn't even close. On average, it was 27.3% better than an augmented version of R0. It just strongly confirms that this combination of difficulty-guided reward and HRPO is what finally unlocks multi-turn search through self-evolution.
And you can actually see this dynamic playing out in the training logs.
Absolutely. The solver achieves its core capabilities incredibly quickly. Its performance often peaks around the 50-step mark, so the end of the very first iteration. The curriculum just accelerates learning that dramatically.
And the entropy plots back that up, right? The solver's uncertainty, its entropy, drops really fast and then just stabilizes. It figures out its policy and sticks with it.
Mm-hmm. But on the other hand, the proposer's entropy and the average length of the questions it asks, They fluctuate a lot more, especially later on. The proposer isn't settling down.
It's still exploring, still trying to find new ways to challenge the solver.
Exactly. It's maintaining diversity long after the solver has locked in its core behavior.
This brings us back to that really crucial insight about scaling. The authors tried different hop ratios in the synthetic data, from an even mix to one that prioritized simpler questions.
And this is a huge finding for the field. The composition of the curriculum matters immensely, and the optimal curriculum depends on the model's size.
So for the smaller 3V model, it was better to give it more simple single-hop questions.
Yes, it needed to build up its foundational search skills first. If you overloaded it with complex stuff too early, it was actually less efficient.
But the larger 7B model was the opposite.
Completely the opposite. It already has more capacity for complex reasoning, so it performed significantly better when it was fed a higher proportion of multi-hop complex data.
So the bigger model needs a tougher curriculum to really unlock its potential.
Exactly. If you don't generate sufficiently complex training data, the larger model just can't take advantage of all its parameters. It confirms you have to match curriculum complexity to the agent's intrinsic capacity.
That's a huge lesson for anyone training these models.
Yeah.
What about the ablation studies? When they took components away, what was the most indispensable part for the proposer?
The initial document context, by far. When they removed the context that seeds the proposer's generation, they saw the single biggest performance drop.
So the proposer can't just invent complex, verifiable questions out of thin air.
Nope. It needs concrete entities to ground its search paths and maintain factual diversity. The format reward was also vital, again, showing that tool use structure is non-negotiable.
Can we ground this in a really complex example? I mean, a 4-hop question sounds pretty intense. The paper mentions one starting with the Australian Labor Party.
It is intense. For a 4-hop question, the proposer has to search for that party, find a related entity, use that as a bridge to another document, and keep chaining these facts across different documents.
Until it finally gets to the answer.
Yeah.
Which in this case was the year the Legislative Assembly first sat, 1989. That's not just recall, that's synthesis.
For sure. And the solver has to be just as sophisticated. Look at the film director question. Which film has the director who died earlier, Gold for the Caesars or Heinz in the Moon?
Right.
The solver shows what they call adaptive retrieval. It uses its internal think blocks to break that down into subqueries. It searches for the director of the first film, finds his death date, searches for the director of the second film, finds that date, then compares them.
And that entire multi-step search and comparison process was learned just from the pressure of the proposer's curriculum.
Oh.
So to bring this all together, Dr. Zero is this remarkably efficient, data-free framework. The proposer-solver dynamic, plus the computational trick of HRPO, it really proves that human supervision isn't a strict requirement for SOTUT performance in these search tasks.
That's the takeaway. Though the authors are pretty candid about what's next, they did see a performance plateau in the bigger 7B model after the second iteration. That suggests there are still challenges in making this kind of self-evolution stable indefinitely.
Like it hits a local maximum instead of just improving forever.
Something like that. And as we touched on, if you're operating completely without humans in the loop, then safeguarding against things like reward hacking and bias amplification becomes absolutely paramount.
Right. It's hard to maintain integrity when the system is its own judge and jury.
Which leaves a really powerful question for you, the listener, to think about. Since Dr. Zero's entire curriculum is driven by that difficulty score, the reward is highest when the solver is struggling just enough. What happens when the proposer evolves to intentionally exploit a vulnerability? What if it starts generating questions that just look difficult because they trigger a single reproducible failure in the solver instead of genuinely creating diverse reasoning paths? How do we enforce honesty? What checks and balances, beyond just format rewards, will we need to ensure the rigor of these agents when their reward is tied to exploiting the other's weakness? It's a fascinating tension that I think is going to define the future of autonomous agent training.